So firstly, I'll give a brief introduction for the Professor Wenbin Yu. Professor Wenbin Yu is from the School of Aeronautics and Astronautics at Purdue University. He received his PhD in aerospace engineering from Georgia Tech and a master degree in engineering mechanics from Tsinghua University. He serves as the director of composite design and manufacturing hub and the CTO for the Anasa Swift company. His expertise is in micromechanics and the structural mechanics with applications to anisotropic heterogeneous materials. He has developed several computer codes which are being used by thousands of researchers and engineers in government labs, universities, research institutes, and companies. He's an ASME Fellow and ARAA Associate Fellow. He served as the chair for ASME Structures and Materials Technical Committee and currently serves as the chair for ARAA Materials Technical Committee and the chair for ASME Aerospace Division. He serves on the editorial boards for 4 international journals and the ASME IMECE Congress Steering Committee. Okay, thank you. I'll give you the Professor Wu to start his talk now. Thank you.
Thank you, Professor Wu. Can you hear me okay?
Yes, yes.
Okay, thank you, Professor Wu, for the invitation and the introduction. I'm very honored to have this opportunity to share my research with the faculty and the students at Cardiff University and some other colleagues. In the recent years, I have been working on the concept of structured genome, which has the potential to provide a unified multi-scale approach to bridging materials genome and also structure analysis. And I know most of you maybe come from the background of the structure mechanics, so I will start from something we are very familiar with, the beam theory. For the beam theory, we start from a 3D body, and we consider the cross-section. Then with some assumptions, we compute the beam constants like extension, bending, torsion, this kind of properties. Then our problem reduced to a one-dimensional problem, which is a set of ODEs. We carry out the microscopic and beam analysis. We can compute the force moment diagram, bending moment diagram, and also deflections. But at the end of the day, we don't stop there. What we do is we want to calculate the stress distributed over the cross-section, use the formula My over I, which we all know to assess the failure with the material fails or not, to check against the allowables. So that's our beam theory we are all familiar with. And if you're talking in the terminology of structured genome, what I'm going to introduce, then from the 3D body to the 1D model is a homogenization process for us to compute the beam properties. Then from what we calculated from the beam analysis, that's our microscopic model, and to compute the original 3D stress distributed over the cross-section is a dehomogenization process. But we are basically considering the cross-section is our microstructure, and the beam reference line is our continuum mechanics model, but it's a spatial generalized continuous model. So the overall, this procedure from the 3D to 1D model, I call it the constitutive modeling. So keep that in mind. Now let's go to the classical laminated plate theory. We're also pretty familiar with. What we do, we start with the Kirchhoff assumption for the kinematics, basically reduce these to be a plane strain problem. And if you carry out the derivations, then we also take the plane stress assumption. If you recall that we didn't take this CIJKL to do our derivation, we use a Q. matrix, which is a plane stress, reduce the stiffness matrix to do the derivation. But we do know plane stress and plane strain, they cannot exist, coexist in the same problem. They are contradicting to each other. But no matter what, we still take these two sets of assumptions and come up with a two-dimensional theory governed over the reference surface. So graphically, basically, we take the transverse normal because what we have is it's basically, in terms of thickness, our ABD stiffness matrix calculated in terms of thickness and the layups through the thickness direction. We'll get the plate analysis. Those are the models governing our plate analysis. After we done our plate analysis, we do the recovery to get the stress distributed at each layers. Then we apply our failure criterion to figure out whether this design is okay or not. So we still have kind of like take the original 3D heterogeneous body, reduce to a two-dimensional surface model. That's a homogenization. Then we also go back to the original 3D stress in the original structure. That's the dehomogenization process. And overall, this part, how we reduce from 3D to 2D is a constituent modeling we are talking about. Some of you may heard about the material genome initiative, and a lot of research has been shifted toward that direction. The main idea is try to use computational tools, experimental tools, and digital data to do the materials development cheaper and faster. But if you look at the research has been done, mainly done at the molecular and atomistic level, and they use tools like LAMPS to do the molecular dynamic simulation. But for our composites, we find out we cannot do at that level. We expect they may be able to get us the constituent models and properties for the constituents like fiber, matrix, and interface. And but from that properties, which Material Genome Initiative can give us as deliverables to construct our models, to do our structure analysis, still a huge gap in the length scale. We are talking about fiber is, about 5 microns in diameter. It's much smaller even than our human hair. But we do know how do we engineer our microstructure in terms of fiber will affect the performance at the system level. At the system level, we're talking about meters. Or if you're talking about wind turbines, you're talking about maybe hundreds of meters. But then you carbon fiber at micron. So you have about 6 order of magnitude difference there. If you are familiar with finite elements, you know that to do a 3D body, you cannot even cross 2 length scales. For example, if you want to capture the details of the carbon fiber, 1 millimeter material block, because you need the finite element size to be smaller than the fiber diameter. So if you do that way, then you find out you're taking about the millions of degrees of freedom. You do just that tiny small material block, then do it at the system level. Clearly, it's not possible. There's some way we must come up with to link from the fiber and to the toes, to the woven fabrics, to the laminas, to the structure components, even to the system level. And what commonly people do is so-called bottom-up multiscale modeling approach. For example, for the unidirectional fiber reinforced composites, what we do is that we take a microstructure to do some micromechanics calculations, then get the laminar constants, then we construct some structure model to do the laminates. So that's what we do, and you have structure mechanics models, micromechanics models. These are kind of like two subjects, and different subjects, they have their own different assumptions, and also there are many theories for either micromechanics and structure mechanics. Could be analytical, could be for micromechanics, could be analytical, semi-analytical, or could be numerical. And for structure mechanics models, you have equivalent single layer series, zigzag series, layer-wise series. That's only for laminates. Okay. There are also all these models have various assumptions involved. I will not mention it here, but there is another more fundamental assumption which is scale separation assumption when we do this problem in these two approaches. For example, that I have a heterogeneous panel like this. If I use this two-step approach, what we end up analyze is a panel with 3 layers and made of 3 homogeneous materials. Then there are issues there. Originally, they basically assume that the layer and layer, they have perfect bonding. Then between the layers, there is no so-called material discontinuity. But now, because of this scale separation, we create artificial discontinuity here. So this scale separation assumption will work if for each layer, there are many fibers inside the layer. For example, for regular composite prepregs, we have about maybe 10 to 20 fibers through the layers. So that's okay for the global behavior, but definitely not okay for the strength prediction. The reason being that the strength is a local phenomenon, and we need to know where the stress, discontinuity, and concentration happens. And by doing this, we have a difficulty to actually accurately recover the stress. That's why for composite laminates, they, buckling, stiffness, and deflection, vibration, this kind of prediction pretty good. But for the strength, still are, or failure and damage, still open question. And for some structures, even this, even for global behavior, is not okay. For example, that we could have a honeycomb sandwich structure. And so if we do this two-step approach, what we do is that we will take the honeycomb as a microstructure to do some micromechanics calculation, get a set of material properties, then treat this as a homogeneous layer, then become a sandwich structure with a homogeneous layer to do the analysis. The problem with this approach here is that we cannot do that way. The reason is that the size of the microstructure is similar as the thickness of the panel. There is no so-called scale separation exists anymore. Both the microstructure of the honeycomb and thickness of the panel must be considered at the same time. And, this kind of thinking also helps us to basically distinguish, to tell the difference between structure behavior and material behavior. This is a paper published on Science on metamaterials 3 years ago. I believe it's a confusion of structure material, structure behavior, and material behavior. What they have a meta structure. When they compress it, you will trace. So they come up and say this is a 3-dimensional mechanical metamaterials with a trace. But this kind of traced behavior only if you have a finite dimension along one dimension. For example, you stack the unit cell along one direction or along 2 directions, you will have that. If you repeat it many times along 3 directions, then you will find out the traced behavior will decay. So this is actually a structure behavior. We know extension and traced coupling can be happen easily with laminates. You don't have to have a very sophisticated metamaterial to generate that. But for 3D behavior, if you stack all these unit cells along all 3 directions infinite many times, the traced behavior will disappear. So that's not a material behavior. So this kind of thinking helps us to find out which is which. So that's the confusion comes from the bottom-up multiscale modeling mindset. So to avoid this limitation of this bottom-up multiscale thinking process, I have been searching for a top-down multiscale modeling approach. But look at the problem from the system perspective. Fundamentally speaking, no matter how sophisticated a system is, it can be considered as a combination of 3D solids, 3D bodies, 2D plates and shells, 1D beams, and thin-walled beams. And geometrically, they have some characteristics. For 3D bodies, you have 3 dimensions all of similar size. For plates and shells, you have the thickness much smaller than the implant dimensions. For beams, you have the cross-section much smaller than the length direction. For thin-walled beams, all of the dimensions, they are significantly different. They are orders of magnitude different. when we do a structure analysis, it's digitalized in terms of elements, finite elements. We have 3D elements, 2D plate and shell elements, 1D beam elements. And what we need to realize is that a single 1D, a line here, 1D beam element could represent a box beam with each layer made of, say, dozens of composite layers. And a single surface element here could be represent a stiffened panel with the skin and stiffness both made of woven fabric, for example. And so how do we basically use this mathematical artifact to capture the reality? That's what the structure mechanician trying to do. And we do know that under each element, each type of element, there is a model behind it, contains 3 types of equations, including kinematics, kinetics, and also energetics, which are the constituent relations. The kinematics and kinetics will remain the same, no matter whether you have composites or have metals, doesn't matter. But what will be different is the constituent relations. For composites, you could have a fully populated stiffness matrix. Even for beam model, you could easily have extension. For example, this S12 is the extension and the twist coupling. So based on this kind of thinking, and we come up with this mechanics of structured genome. Basically, look at the system level, what the type of model you want, and look at what would be your inputs, how your material is characterized. Then basically you have 2 model representations. What we need to do is minimize the information loss between these 2 models. And some of these, we already applied this method to various type of problems and developed several series. They are implemented into the code called SwiftCom. This MSD establishes a formal framework that does not exclusively rely on direct information passing across scales, but rather operates from the homogeneous behavior and captures the details at scales relevant to your design. So let me illustrate more details about that. So the basic idea is we are still within the continuum framework. So start from the original 3D continuum mechanics. First, we need to start identify what will be the structure gene. And then we will use the principle of minimal information loss to mathematically decouple the original problem to a constituent modeling over the structure gene and also a structure analysis. The constituent modeling provides all the material properties you needed or structure properties for the structure analysis. Structure analysis usually done by commercial finite element codes like Abacus, ANSYS, this type of codes. And from the structure analysis, you will get the global behavior, and then based on the global behavior, have the information from the constituent modeling. We will carry out the dehomogenization to get the local fields, what are of our interest to access failure and all that. And the advantage of this is that we confirm all the approximation happens at the constituent modeling and also guaranteed to be the best by the principle of minimal information loss. And the structure analysis can be formulated as exact as you want. It could be geometrically exact, and also it's available in standard finite elements codes. So to use this framework to do model scale modeling or construct structure models, we need to ask 3 questions. First, what is the model I want, microscopic model? What is my original model, basically to capture my physics? And it could be elastic models, could be plastic models, could be viscose elastic, depends on your behavior, on the behavior you want to capture. Then what is the structure gene? And really, what's new is the structure gene here. A gene, we know it's a language of DNA that serves a set of information encoded in the blueprint for an organism's growth and development. The word gene, basically, when we apply the in the structure modeling concept, connotates a smallest mathematical building block toward a larger purpose. So what you need to memorize is that the structure gene is the smallest mathematical building block of the structure. So So keep that aside. Then once you answer that 3 questions, what I just mentioned, then there are 3 very basic steps of using MSD. First is to express the kinematics of the original model in terms of the microscopic model. So you can express your real displacement field in terms of your beam displacement plus something you don't know. Then you can derive the stream field and in terms of the stream field of the global model and something you don't know. Then you express the information of the original model. For example, if you're talking about the elastic behavior, we are talking about the potential energy express in terms of the kinematic variables of the model you want. And you with unknown. How do we solve this unknown? Is to minimize the loss of information. Because you have 2 model representations, basically. This is the original model information. This is the model you want, and you need to minimize the loss of information that can help you to solve for your W, which is unknown here. So that's pretty clear and straightforward. I would need to explain how the structure gene concept works. For 3D elements, for example, we want to do a 3D solid analysis. And it depends on the material makeup. If it's made of a layered material, for example, a binary composite, then your smallest mathematical building block will be these 2 segments. Because I can use these 2 segments, sweep in plane to build this binary composite, then repeat the binary composite through the thickness, build the entire block. And for fiber reinforced composites, all I need is a 2-dimensional domain, because I can extrude the 2-dimensional domain along the fiber direction to build that slice of material, then sweeping along the in-plane direction to build the entire layer, then build the entire structure through the thickness. And if I indeed have 3-dimensional heterogeneity, then I deal with a 3D block, like a particle reinforced composite. At the end of the day, what we want is for example, linear analysis for 3D solids. We need a 6x6 difference matrix. Out of this 1D domain and 2D and 3D, we'll get 6x6 difference matrix and do the global analysis. Then after we done the global analysis, then we should get whatever happens inside the original structure, the 6 stress components, string components, and all that. So you will find out this is basically a general purpose micromechanics application. But you do realize that some of you may be familiar with RVE analysis. Only this is close to RVE analysis. RVE analysis also deal with 2-dimensional analysis, but they only get the in-plane properties and also can only get the in-plane stresses. And for the purpose that some of you may be familiar with RVE analysis, I want to do this comparison of these 2. RVE analysis, if you have done it, then you know the tricky part is the boundary conditions. And for this MSD-based micromechanics, we don't have to explicitly apply the boundary conditions. And also the Hill-Mandel condition will be automatically satisfied. We don't have to do the pre and post process. What do I mean is here that for RVE analysis, what we do is that we have a block of material, we create a set of boundary conditions in terms of displacements and tractions. Then we do the analysis, then we calculate the average stress and average strain to get the material properties. But for MSD, what we compute is the material properties directly. And the 6x6 difference matrix, for example, is semi-analytical. It will be converged faster than the RVE analysis because we don't compute stress and strain, then get the material property. We can get the 3D properties and 3D local fields out of 1D or 2D or 3D domain. For example, that a lot of RVE analysis, if you want 3D properties of this fiber reinforced composites and 3D stress, you need to deal with a 3D block. But using our approach, you only need to do a 2-dimensional domain. And we can compute the complete set of 3D properties using one analysis. When you do RVE analysis, you have to apply the load in a certain direction, carry out the analysis, get the material property along that direction, and then you do another one. So you at least need to do a 6 analysis for 3-dimensional properties. Okay. Yeah, there is a little bit of technical glitch there. And it's also more versatile. It's a single cell for all heterogeneous materials, could be periodic and partially periodic or aperiodic materials. And also the HG, you know, RVE would be kind of like a rectangular cube, but HG can have aperture shape. Depends on how your microstructure looks like. And it will be more accurate. We show that for 3D periodic materials, it can achieve the same accuracy as RVE analysis and also as asymptotic homogenization. And for partially periodic and aperiodic materials, we can achieve the best accuracy because we use the principle minimal information loss. For example, for the simple problem, we want to get the 3D-dimensional properties of a laminate. That's the black aluminum approach. The conventional approach, what we do is that we use the classical lamination theory to get the in-plane property, basically calculated from the A matrix. The out-of-plane properties, we take some type of assumptions, like the constant stress through the thickness. But if you use the MSG, what we need to ask is that what is the original model? The 3D elasticity model with layer-wise heterogeneity. What the model I want is a 3D model with homogeneity. Then what would be my smallest mathematical building block is that the transverse normal lines through the thickness. Then what we need to do is write out the energy of this guy, write the energy of this body, minimize the energy loss. We'll find out what would be the 3D properties for this black aluminum without take any additional assumptions here. How about if I have a panel but made of heterogeneous materials like the sandwich structures, like the corrugated panels, like stiffened panels? The idea is still the same. What would be the smallest mathematical building block for this sandwich structure or laminates? We have the transverse normal line to be the SG. If I have heterogeneity along one of the in-plane directions, I will have a two-dimensional domain to work with. If I have the heterogeneity along both directions, I will have a three-dimensional domain to work with. What I want is the plate constituent relations. If we're dealing with nonlinear analysis, we need the tangent stiffness matrix. And to carry out the plate analysis depends on your model, whether it's Kochikov-Love model or Reisner-Mindlin model. And after we get the constituent model, we do the plate analysis and get all the behavior you want. Then what you need to find out what the stress happens at the original structure. So out of this one-dimensional SG or two-dimensional 3D SG can deliver us, for example, for linear analysis, the ABD matrix. So that is basically provide us a consistent way to construct the plate and shear models out of all kinds of structures. And that's one way, and it's a very systematic and uniform way. And another way is that another point I want to make is that if we view this two-dimensional surface as a general continuum, then every material point, you have a corresponding microstructure to help calculate the equivalent or effective properties. This is a plate or shear properties for this continuum. So in that sense, what it says is that this plate and shear theory we know traditionally belongs to structure mechanics. Is actually a special application of micromechanics. You still have a homogenization going on. Basically, this line homogenized to a point, and this block of two-dimensional domain homogenized to a point. This three-dimensional domain homogenized to a point. And now let's look at this classical lamination, laminated plate theory again. Conventionally, we say that the Kochikov assumption and plane stress assumption, then you use variational principle to derive the equations. And to use our approach, you will find out you list what would be the original model. Okay, then what would be the model you want, which is a two-dimensional classical plate model. And both you could have their potential energy to write out. Then you minimize the energy difference, you will derive these equations. at the plate level without the Cauchy-Hoover assumptions and plane stress assumptions. What it means that the strain field could be three-dimensional and stress field could be three-dimensional. And how about if you have a very slender structure component like helicopter rotor blades? What you will have is that, for example, if a slender structure have a uniform cross-section or can be approximately considered as kind of like combined of different segments of uniform cross-section, then cross-section become your structure genome, your microstructure, and to calculate the beam properties for your beam analysis. If you have heterogeneity along the length direction, then you deal with a 3D block. Out of this 3D block, you will calculate the torsional stiffness, bending stiffness, extension, all the couplings to do the beam analysis. After you've done the beam analysis, you can do a recovery to get a three-dimensional stress within the original structure. For some of you who are familiar with my work, this is actually what I originally studied when I was a PhD student at Georgia Tech. We have a code called WEBS, but it's only dealing with the cross-sectional analysis and for a beam. And it is a unique technology, and it has been continuously funded by Army over 3 decades. And also, it will currently we still have a project to make the code available for the Army folks to do the design optimization of composite lifting bodies. Now it becomes a tool of choice for helicopters and also wind turbine companies. It provides an efficient, high-fidelity solution for slender parts. And as long as you have one dimension much larger than the two other dimensions, that basically is a beam theory. The advantage of our beam theory is that because we don't take all kinds of assumptions, we just put it into a beam model with the principle of minimal information loss. And the accuracy is almost as similar as a 3D FEA if you can spend the time and the effort to do the analysis. Next, I will show some applications we have right now. One is the NASA game change development deployable composite booms. If you look at the booms, that it's kind of like a beam structure, but the problem is that it's supposed to be straight, but when they store it, they get coiled together, store it in a satellite, then deploy it, right? Then when you deploy it, actually it could become kind of like bent. And how do we predict it? Because it's a time-dependent behavior, then viscose elastic, and we did a simulation for them. They treated this as a shell, but each shell layer is made of woven fabric. So we can directly compute the viscose elastic equivalent shell stiffness to put into abacus as a UMAT to do the UGENS to do the simulation of the test they use to characterize this type of structure. And we also did a simulation of the global kind of like oiling of the structure to the hub, and also deploy. And you will find out what is below is the deployment of the entire boom and how it happens. And we try to find out, what would be the weird behavior happening, kind of like create a virtual train for this system so that they can reduce the number of experiments they needed, and also try to come up with a system which will function as designed. We're also working on something called homogeneous element. It's very different from the traditional multiscale modeling. And what this idea is that I have a heterogeneous system. It's discretized by a block of 3D elements. But when you put to the entire system, it's just too large to analyze. So can I homogenize this block of elements into one single element? The advantage of this is that the traditional multiscale modeling then all the microstructure is considered as a point in the global model, which is, only if the scale separation is valid, then otherwise that is not true. If we do it this way, then the finite size of the microstructure retained. We didn't change the size of the finite elements, but what we changed is that we try to capture the heterogeneous details of the original heterogeneous body and using a homogeneous element. And what we will have is that we will have an effective element stiffness matrix. And this, then you do the homogenization of this one. It will give you an effective element stiffness matrix. For example, if it's 20 loaded element, then you're talking about 60 by 60 stiffness matrix. If you're 8 node brick element, you're talking about 24 by 24. And then you can do your global analysis. And after you do a global analysis, you get the nodal displacement, then you can do the homogenization. You can get the stress in the local fields. And still what happens, how do we do the homogenization? Dehomogenization is through the minimization of the information loss. We know that this homogeneous system will lose some information, but we don't know how it will be lost. So that's the idea, and we had the example like this. We have 3 different layers, and originally we have a lot of elements here to do a DNAs. But we can use a simplified model, only use 40 MSG-based elements, okay? Or maybe we can do a little better because usually homogenized elements do not have a good capability to handle the boundaries. So the boundary part, I still use the original elements, but the middle part, I use the homogenized elements. Then you will find the results that comparing to the DNAs, which is many elements, hundreds of thousands of elements, and compared to the pure UEL and also partial UEL, you will find out the pure UEL is already pretty good. But for some small terms like the transverse shear stress and normal stress, then partial UEL, which is 2 boundaries, I still use the real elements to handle. In the middle, I use homogenized element to handle. It will become much better comparing to the direct finite element analysis. And also in these days, I think a lot of people spend the effort to do the machine learning. And we also did some work there. And our idea is that how can machine learning to help solve the problems we haven't solved. And to put it into perspective, I use a very brief science history you are all familiar with to illustrate the different use of machine learning and artificial intelligence, and also our structural mechanics and micromechanics. So I think the first person is Tycho Brahe, and the second person is Kepler, and then Newton. I think the reason I put these 3 guys here is that they represent a very interesting point in science. We know Brahe did the observation how the heavenly bodies move, and then it's Kepler who take the data, did the curve fitting, come up with the three laws we all know from our high school physics. And it was Newton to come up with this law of universal gravitation to basically find out it not only applies maybe to the heavenly bodies and also all the other bodies, which means the Newton's laws, F equal to ma, everybody knows. But for Kepler stuff, I think most of us heard about the name, but we don't know what it is now. And Brahe's data is long gone. We even don't know where it is. So what I'm trying to say is that, machine learning, if Tycho Brahe's data still exists, I think it can be based upon what Kepler obtained and not go beyond that. they cannot, you have the data there, the raw data. So that is basically machine learning. It's generate kind of like empirical knowledge. Of course, with machine learning, you don't need a genius like Kepler to do this curve fitting. But to come up with the Newton's types of knowledge, really need a human beings. Is epistemic knowledge. And also what we learned in our classrooms, don't think that the machine is going to replace everything. The real physics, like say Newton's law, like the geometry, I think those still are good. Will not be and should not be replaced by data-driven science. That's my point. So when my students come to me, they want to do machine learning, I say, where do we need help? First, computing time. When you do multiscale modeling, you will find the computing time will be a limitation. Then second, the assumptions. What will be the constituent models and properties for our fibrous matrix or laminars? The failure criterion is a human-made assumptions. Delamination criteria, for example, and also the assumptions on geometry and topology of microstructure. Then how can we help? How can the machine learning help? It will reduce the time by replacing physics-based multiscale models, use surrogate models trained by machine learning. And also it can learn the microscale models and the properties using major data at a microscopic scale, like structure behavior, by physics informed and physics constrained or physics guided machine learning. It can also construct digital microstructure out of the major data used in machine learning. So when we use machine learning, we don't use machine learning as a black box. We break them down so that I can still take my geometry, screen displacement relations, and my equilibrium equations. What I don't know is my constituent relations for whatever my input of multi-scale model. And currently we have been working on basically how do we basically using abacus together with machine learning to train my material model, use data happened at the structure level. So that's what we have been doing. If you're interested in more details, we have published a few papers on this in this direction. We are not only dealing with theories, come up with ideas, we also do technology transfer. Some of you may know that we made our code freely available on CDM Hub, and we integrate our code with Gmesh, is another open source code. You can do all kinds of microstructure, even with say honeycomb sandwich structure to get the plate properties or three-dimensional properties. We also integrated our code with TextGen to deal with woven or braided composites, two-dimensional or three-dimensional. And that's available for everybody to use. You just need to create an account on CDM Hub. And we also have an app available on iOS or Android. And you can download the code and it can do all types of calculations we encountered in composites. And we also, as I mentioned, the Army project basically integrate our code into the Galaxy rotor design optimization framework. That's what we are doing right now. And we also integrate our code with CATIA so that basically you can take a cut of the cross section, then it will call our code to calculate the cross section property to figure out where the shear center and the extension center is. And we also integrated with Altair products, OptiStruct and HyperMesh. And we integrated with Abacus and ANSYS and the Nastran so that make it easier for other people to use who are familiar with this kind of commercial finite element codes. They can directly take this kind of like a plug and play module to get the capability to handle highly heterogeneous and anisotropic systems with microstructures, and they still make use of your standard structure elements we have in this course. So as a conclusion, that the mechanics of structured genome bridge the gap between the materials and structures to harvest to harvest the full benefits of Materials Genome Initiative. It provides a unified modeling for structures materials, featuring anisotropy and heterogeneity. It eliminates invalid scale separation assumption and also assumptions within the scales. It can achieve the direct numerical simulation accuracy and the efficiency of engineered models. It enables us to model composites as simple as metals and capture details as needed and affordable. And also it powers conventional structure tools with the accurate constitutive modeling for anisotropic heterogeneous materials and structures. And you don't, a lot of structure mechanics models, they develop models, but they cannot make use of the existing abacus and ANSYS structure elements. And last but not least, maybe the most, is that the MSG unifies micromechanics structure mechanics for multiscale constitutive modeling. And Jacob Bryanowski, in his book, The Creative Aspects of Science, he said that the progress of science discovery at each step of a new model, a new order, which gives unity to what had long seemed unknown. Already, a close link between electricity and magnetism. Maxwell did it when he linked both with light. Einstein linked time with space and mass with energy. So science is nothing else than search to discover the unity. And with the mechanics of structure genome, you will find out that we provide a unified approach to deal with micromechanics aspects of this heterogeneous materials and structures, and also plate and shell modeling, and also beam modeling, and also doesn't matter what kind of microstructure you will have. And this is the last slide I have, I believe. This is a chart showing that what this method can do, and basically it can be used for virtual testing of the materials and also structures for that perspective. It can also do multiscale modeling of structures, and not only the laminates, but also stiffened structures, build-up structures, sandwich structures, and all that. Those are the structure genes, or the microstructures, if you want to call, we played with. And it can be any upstream microstructures. But it all come up with the same idea, the principle of minimal information loss. Once you know where the model you started and what kind of model you want. And this mechanical structure genome provide a theory for you to do the derivation of structure series or materials series. So mechanical structure genome is kind of like a series of series. So with this, I will stop here and take any of the questions you may have. Thank you for your attention.
Okay, thank you very much for Professor Yu's presentation. It is very interesting talk. So any questions from our audience? No? Any questions? Any technique or general questions? You can unmute yourself directly. Okay.
And also you can type the questions in the chat box. I can monitor the chat box if you don't want to ask.
No, okay, I'll give a first question. So, so basically, for my understanding, is that the probably not accurate, but my understanding is that when you apply the structure genome method, is that you replace the conventional structure analysis in the either node or element using additional routine or additional modeling procedure to represent that representative part of the constitutive equations or the work out the equivalent stiffness matrices for the material from the materials. Is that the way how the key method? How
yeah, let me use my second slide to show that.
Yeah, this one. Yes.
Yeah, let me do this one.
Yeah.
Okay. When you look at here, that's the traditional way to model, right?
Yes.
What we can do is that we basically in MSG, because we don't know, this is based on the assumption, but you basically need to add some unknown functions here, W, W1, W2, W3. They're three-dimensional functions. And you don't know what it happens. So you still use this, that's a simple enough example here. You still use these constitutive relations to carry it out, like I read out the energy of my original three-dimensional model. And of course, now I will have curvatures, impedance strengths, but I also have unknowns. How do I get rid of these unknowns? I need to minimize the loss of information between whatever my original three-dimensional model and two-dimensional surface model. So basically, this is by assumption to get rid of those. But there is no reason to say that, for example, the transverse normal should be rigid. Because you have plane space assumption, then they're free to move. And you cannot make that. So basically, this MSG come up with a method to remove this common structural assumptions like the Cauchy-Love assumptions or the Bernoulli assumptions, like the even layer-wise or all the higher order assumptions. Why they should be, behave like a certain polynomial. Those are all assumptions. Some of the assumptions works okay, but also this kind of assumption you'll find out it only works for laminates. If you have a stiffened panel, you have difficulty because you don't have a thickness exist in that model.
So so you eventually you after this homogenization procedure by the structure genome method is eventually you're solving a 3D full 3D mechanics problem. Is that true?
No, it's not to solve a full 3D mechanics problem. If you look at here, and let me see here. So for plate, I think you're familiar with plate.
Yes.
We solve a one-dimensional problem here, and two-dimensional problem here, and three-dimensional problem here. But we solve problem is another traditional stress analysis. We compute the spin energy, for example, for linear behavior. We will find out what will be the spin energy can be represented at this level.
Yeah, so after
it's not
this
procedure,
so that's what I'm asking. After this, this procedure, the eventual, the conventional, it will input into the conventional structure analysis.
Yeah. Yeah. If, for example, you will put it as a section stiffness for abacus to carry out this analysis. After you done this analysis, there is a dehomogenization, which is a very simple procedure to get the stress at which point you need it.
I got it. Okay. So in this procedure, the unit analysis procedure, you're solving with no assumptions, no conventional assumption. It's a full.
Yeah, that's correct. That's correct.
Okay.
Yeah.
Okay. Thank you very much for your explanation. Is anybody else?
Yeah. Usually usually traditional approach, they make some assumptions to get from here to here.
Okay.
Certain assumptions. So there is not a mechanics theory really governing that.
Assumptions. Yeah. Okay. I got it. Yeah, I got it. Oh, okay. Okay. Is anybody else have any questions regarding Professor Yu's presentation? No. No further. Okay, we just finished. Okay. Let's thanks again for Professor Yu's presentation give us today. Thank you very much. So hopefully we can build up some future collaboration between Cardiff and Purdue University.
Yeah, and also take a look at the code on CDM Hub. I think that you need to experience that. For example, that how do you can directly from CDM Hub, you can create a block like this, get the torsional stiffness of this block.
Yeah. Yeah, this is eventually move to the beam structure, but you model the either 2D structure genome or 3D structure genome, depends on the practical structures, geometry, and the configurations, the practical configurations. Yeah, that is a very good idea. Yeah, it's a very good idea. Great. Yeah. Yeah. Okay. Thank you. Carol, do you have anything you want to talk?
Yes. Thank you for Professor Wu for your invitation, and thank you all for the attendees who take the time to attend this lecture. And you can contact me if you are interested in this line of research.
Thank you very much.
Thank you.
Thank you, Carol.
Thank you.